got a subset of x. Did it shut itself off?
No, we're good.
We're good? Okay. You have a subset of x, an element in x. What does it mean for x to be, little x to be an interior point of E and a limit point of E? It's going to be an interior point if there exists some open ball of some radius centered at x. So that open ball is a subset of E. You could use this notation in general. If I ask you this in terms of the real line, which is the way to phrase it, then you should be able to use interval notation for your open ball, quote unquote. You should be flexible enough to either do this on the real line or in a general metric space. I might ask you the definition in either situation. And with a limit point, you should be able to do it either notation as well. With x is going to be a limit point if for all positive r, the intersection of this set with E, x will be a limit point of E if this intersection contains at least one point other than x. Or if you take out x out of the open ball, make it a deleted neighborhood of x, and intersect with E, that's going to be non-empty, would be another way to say that. But again, you should be able to write it with intervals on the real line as well. The intervals like this are your open balls. One-dimensional open balls. Then an open set is a set, you can think of it right away, that such that every point in the set is an interior point of the set. And a set is closed if it contains all its limit points. E prime is the notation for the set of limit points. A set E will be closed if E prime is a subset of E. It contains all its limit points. Every limit point of E is in E. And that definition works whether you're on the real line or in a metric space. I often, in the past, have given a few problems where I ask you to identify, for a given set E, what is the interior of the set, what is the derived set, and what is the closure. Common examples include E is an open interval or a closed interval, or a half open, half closed interval, which in the real line is neither open nor closed, as a subset of the real line, in the topology of the real line, standard topology. I've often given examples like E could be the rationals, or E could be the irrationals, or E could be a set of numbers of the form 1 over n, for example, or something analogous to that. Or maybe I union this with 0. I did discuss examples like that in the lectures. You should be able to handle two-dimensional examples. If E, I can describe it with, okay, let me draw it first. Say you've got a disk, maybe where you include the points on the top of the disk, but not on the bottom. That could be E. In set builder notation, you can say this is it's the unit disk centered at the origin. The set of all points x, y, such that what do we say this here? Maybe x squared plus y squared is strictly less than 1 when y is strictly negative. And less than or equal to 1 when y is bigger than or equal to 0. That could be a set builder way of describing this set. It's neither open nor closed. What's its interior? Its interior would be the open disk, not including any of the boundary. The closure would be the closed disk. The derived set would also be the closed disk. E bar, by the way, in case you forgot, is always equal to the union of E with the derived set. That's true always. That's the definition of E bar, the closure. The closure can also be thought of as being the smallest closed set containing a given set. E is always a subset of E bar, and E bar is the smallest by set including smallest closed set that contains a given set inside it. But they're going to be equal if E is closed. Got some exercise references on 2 examples like this. These exercises are in exercise section 8.1. The definition of a limit point that I described a few minutes ago is equivalent to saying there's going to be a sequence of points in the set that converges to that limit point of the set. Remember I said little x is a limit point of set E if for all open balls around x of any radius, that set contains points in E other than x. That statement is equivalent to saying x is a limit point of E if there exists a sequence of points in E converging to x. So that sort of justifies the definition of that of calling it a limit point. The complement of an open set is closed, and the complement of a closed set is open, and the proof of that, we did talk about that proof in the context of metric spaces, I believe. I think it was Monday, 2 lectures ago, I think. The union of any collection of open sets is open. The intersection of any finite collection of open sets is open. The intersection of any collection of closed sets is closed, and the union of any finite collection of closed sets is closed. Those are facts to know. You know, since some of these facts don't really have names, maybe I give it to you more as a true-false kind of thing in a closed proportion. Should be able to prove this or some piece of this. Proving it all would take too long. I did talk about the proof of this in the very first lecture on topology before Thanksgiving, although it was in the context of the real line. It was the first lecture we had. I was talking about important subtle properties of open intervals and unions of open intervals, intersections of finitely many open intervals. The very first lecture on topology before Thanksgiving. What would that have been? Lecture 31 or something? 32? Something like that. I talked about that then, and we went through the proof. It's true in a metric space as well. The proof doesn't really change much. You just use open balls rather than open intervals. Without peeking at page 295, find an example of an intersection of a collection of open sets which is not open, and a union of closed sets which is not closed. Can you think of an example right on the spot here? If it's going to be an intersection of open sets that's not open, it's going to have to be an infinite intersection, an intersection of infinitely many sets. Here's one such example. Probably the simplest example. The intersection of this is just the 1 point set 0, which is closed, not open. Which brings up a point, sometimes I also give examples with E that consists of, say, finite sets. you should be able to find the interior, the derived set, and the closure of finite sets as well. Every open interval is an open set, and every closed interval is a closed set, and more generally, every open ball is an open set in a metric space, and every closed ball is a closed set in a metric space. And we did prove that in class. We proved every open ball is an open set. And I think one of the completion problems is to prove, for your journal, every closed ball is a closed set. I remember writing a key for that.
So if we have like copies of our journal stuff, is that fair game for like the notes on the test or not?
Yeah, you can use anything you want in the test. I might, for example, if I put a proof like this on the test, I might make it a specific open ball, like a radius 7 or something, which theoretically makes the proof a little simpler, but you have to figure out how to modify it. Another example I could think of possibly putting on the test is to prove, for example, that a half plane with the boundary missing, boundary not included in the prove that's open with the definition of an open set. Prove every point's an interior point using open balls, open disks, and so that could be another example I could give you. That's not one of the completion problems. What is, and that, I mean, you should be able to deal with that. To prove something like this is an open set in the plane. Another question?
How much of the test is going to chapter 8, which is
Well, the entire closed book portion, and probably 20 to 25% of the open book portion. So it's a major part. That's just a rough guess with the open book portion. Every open set can be expressed as a union of open sets. It's also true that every open set, in the real line at least, according to our book, can be expressed as a countable union of disjoint open intervals. That's referring to the real line. It's actually relatively easy to prove every open set is the union of open intervals, or in general, in a metric space, every open set is a union of open balls. Actually, one of the completion problems is to prove that every open set in a metric space is a union of closed balls. They're both true, which seems a little weird, but it's not too hard to prove once you see what to do. If E is an open, or if O is an open set in a metric space, for each X and O, you can find an open ball of some radius called the radius R sub X that's entirely inside O. And essentially, it's the union of those open balls as X varies over O that also equals O. And you could take this to be a closed ball as well, maybe of a smaller radius, to make sure it's inside O, and get O as being the union of a bunch of closed balls. That's one of the completion problems, was to prove that an arbitrary open set in an arbitrary metric space is a union of closed balls, but it's also a union of open balls, which are open sets. And closed balls are closed sets. Okay, more problems about identifying interiors, derived sets and closures. They include exercises 25, 26, 27, 35, 36 in section 8.1. Compact sets. What is an open cover? What's a finite subcover? And what does it mean to be compact? A set is compact if and only if every open cover has a finite subcover. So once you have the idea of an open cover and a finite subcover, the definition of a compact set is easy. It's very short. Our book, again, writes that definition in section 8.2 in terms of open covers that are open, consist of open intervals. However, in metric spaces, this definition still holds. A set in a metric space is compact if every open cover has a finite subcover. The book gives a lot of examples. I didn't take the time to do so of open covers of sets because it's kind of a confusing concept at first. So you should study those examples, section 8.2. Look at those exercises. You should know that every compact set is closed and bounded. Yeah, I guess it's feeling like more with theorem statements. It's got to be a true-false kind of thing, except for perhaps the generalization of the extreme value theorem is something that I gave it a name to. Or maybe I kind of described the theorem. Well, the Heine-Borel theorem is another name theorem. We'll come to that. This is related to that. Every compact set in any metric space actually is closed and bounded. What do I mean by understand exercise 9, but it won't be in the test? Section 8.2. I wrote this last year, so I forgot what I meant. Finish the proof of theorem 8.11 that a compact set is bounded. Okay. So essentially what I'm talking about is showing compact sets are bounded is not going to be on the test, not one of the proofs of the test. But you should know this fact. Closed subset of a compact set is compact. Another fact. This is a kind of fact that might be easy to forget. Not sure if I'll put that in the exam or not. Here we go, Heine-Borel theorem. Down here, let's look at that first. A set of real numbers is compact if and only if it's closed and bounded. And its generalization, not to an arbitrary metric space, but to arbitrary Euclidean space, Rn. It is true in Rn with the standard metrics. And in fact, any one of those P metrics is equivalent in that kind of metric space as well, because they're all equivalent to the standard metric, the P metrics. Remember what I'm talking about, the P metrics, there was the P norm. I think that was lecture 34 or something. This is true in the real number line, it's also true in Rn. It's not true in a general metric space. We already said compact sets are closed and bounded, but in a general metric space, just because a set is closed and bounded doesn't mean it's compact. So that's a name theorem you should be able to state it, and also in general case for Rn. Any intersection of compact sets is compact, and a finite union of compact sets is compact. That's proof. I put this on here last year. Maybe this was a couple years that I wrote this. I'm thinking I didn't really spend any time with this at all, so I'm going to go ahead and delete this. And maybe for future classes too. Maybe, maybe not. Continuous functions, that was a big emphasis. Back on our lecture before Thanksgiving, I think I mentioned this one. A function's continuous on R, I'm assuming it's defined on all of R, if and only if the inverse images of this form, the pre-images, where you've got open intervals there, are open in R for all A and B with A less than B. The book uses the word inverse image. I wrote inverse image there. I really prefer in general using pre-image for the name of that. This is the set of all points that get mapped to the interval from A to B. This fact is generalizable and true in metric spaces. Let me write the form for metric spaces. This theorem, we didn't give a name to it, but I think this theorem is important enough that I'm about to write on the board that maybe you should be able to write it down if I briefly describe to you what I'm hinting at, wanting you to write down. If I say you got two metric spaces, xd and y rho, and you got a function from x to y, I'm just emphasizing their metric spaces here. I'm not going to use d and rho in the theorem statement. I could say, write down, let's describe it this way, the preimage condition that's equivalent to continuity on x. Here it is. Theorem. That's the preimage condition for continuity of f on all of x. F is continuous on x, if and only if. It is an if and only if theorem, and you should know that. For all open sets O in Y, the preimage set of all points in X that get mapped into O under F is open in X. That's the theorem. We proved this using the metrics. I think it's an if and only if so. It was a two-part proof. I think one part of that proof could show up on the test. It's in your notes. You could technically use your notes if you took good notes. Could show up on the test. It's a little tricky, but I mean, just mostly its difficulty arises from its abstraction. The trickiness is in the abstraction. As far as the steps to do, once you know the definitions well, it's pretty straightforward. Like, what is an interior point with open balls? The notation gets a little tricky. You know, is this an open ball with respect to D, or am I talking about an open ball with respect to rho? The D or the rho should be the subscript, depending on what you're talking about. That's pretty much the same as this column there. Okay, here we go. Here's our generalization of the extreme value theorem. Partial generalization. The direct image of a compact set under a continuous function is compact. And we proved that in class around either last Friday or Monday, I forgot. 2 or 3 lectures ago. How did it go? You got to use the definition of compactness. And the definition of compactness, once you understand it, is set up to make this a relatively easy proof. Relatively straightforward. It's set up that way. How do you do it? Let me just draw a diagram. Here's X. Here's Y. Here's some compact set K. F maps X to Y. Here's the direct image of that compact set K. It's denoted F of K. You want to show that's compact? Give me some open cover. An arbitrary open cover of this that could have uncountably many sets in it. Do something like capital omega for your index set. It's a collection of open sets that covers that. You got to use the compactness of K, so what you have to do is you have to pull those open sets back to X using the preimage idea. The preimages of all those open sets, because F is continuous, each preimage is open in X. And the union of all those things contains K. That needs to be proved. But definitely they're all open sets because F is continuous, and because of this theorem. K is compact. There must be finitely many of those that cover K. Call them G sub alpha 1 through G sub alpha n. Now push those sets back over here. F of G sub alpha 1 through F of G sub alpha n, and prove that that collection of finitely many open sets covers F of K. So it's sort of a back and forth kind of thing, using the compactness of K. And again, the definition of compactness and strangeness is exactly what you need to make this proof really relatively short in the big scheme of things. By the way, this theorem is a theorem for us for metric spaces. Just for your information, in general topology, even topology where you're not talking about metric spaces, but just sets with collections of open sets, this theorem becomes a definition of continuity. You don't need to know that, I just want to re-emphasize it one more time. I did mention there's a generalization of the uniform continuity theorem, but that won't be on the test. And I said that a couple years ago, but I'm saying it now too. I'm not going to test you on that. But this thing was the generalization of the extreme value theorem, and you should know that's what it is. And you should know why. And it is a partial generalization because compact sets don't have to be connected in one piece. You know, the extreme value theorem on the real line essentially says the direct image of a closed interval is another closed interval. Closed intervals, by the Heine-Borel theorem, are compact. Closed and bounded intervals, I should say. But this theorem here, oh no, not that theorem, but the theorem I was talking about proving up here, says the direct image of a compact set is compact, but how do you know it's one piece? You know, why couldn't this be two pieces? Continuous functions also preserve what's called connectedness of a set, which if you did read the first few pages of section 8.4, you should remember that's in there. That's not going to be on the test. But that was a concept that also is needed to generalize the extreme value theorem. And something that's not on here are other things we talked about with metric spaces, other examples of metric spaces, which did include the symbol space, points that are sequences of zeros and ones. Also included function spaces, like this one. Set of all functions, continuous functions defined in the closed interval from A to B. And norms, the suit norm. And how that leads to a metric. You know, our book doesn't talk about norms, but I did, and I think it's a good idea to talk about norms in the same context as, similar context as metrics. And now once you've got this norm, you can use it to define a metric as just take the difference of the two elements and take its norm. Anytime you have a norm, you automatically have a metric. It doesn't go the other way. Anytime you have a metric, you don't necessarily have a norm. Norm measures the distance to zero, and your space might not have zero in it. The number 0 or the vector 0. So metric spaces don't necessarily have norms, but all norms lead to metric spaces. And we proved things like the triangle inequality in this context, which that could come up in the test. So there's a lot. We're pretty efficient, I think. We covered point set topology, the basics and most fundamental things in 5 lectures. I think we covered it pretty nicely in terms of getting the main points across. And it's a lot that we did in just 5 lectures. Our 6th lecture was the application. You may want to rewatch those lectures. Just understand. What else is on the test? Oh boy, the rest of the book. I will pick and choose certain things, and I don't necessarily know that I'll necessarily tell you the exact types of problems, but maybe general types of things. Probably, I'm guessing there'll be something where you've got to use the definition of a super and inf, but not necessarily. I'm not guaranteeing that. Maybe I give you a sequence. You got to prove the sequence converges. I give you a direct formula, or prove it's Cauchy. Or use the fact that bounded and monotone sequences converge. That's a fundamental fact to be able to use. Cauchy convergence criterion, you might need to use that. Those are all pretty fundamental things. Definition of a limit of a function. Chapter 3, we're talking about function limits, not sequence limits. Using the epsilon and delta definition. You can see putting that, a problem like that in the proof. With derivatives, you should be able to use the derivative rules. Just to review some calculus, you should be able to calculate a derivative with a limit. Should be able to use the mean value theorem in proofs. It's a lot. Chapter 5, I think I'd mostly test you, if anything, on the fundamental theorem of calculus, both parts. It won't be a statement, but maybe if you use one or both parts. Chapter 6 and 7 were about sequences in series, numerical series, and sequences in chapter 6, and then functions in chapter 7. Yeah, I think I have to write the test and then just tell you. Maybe I'll tell you some things you can definitely rule out. Maybe I will tell you some specific types of problems that could be on the test as well, the open book portion. I'm not sure. It depends on how the test takes shape, which I need to work on here. So there's a lot. This is it's a challenging course, and Annie's got a shirt, right, that she sent you. I survived real analysis. Is that right? Is that what it says?
Yeah.
Okay. Making it through this course is it's a good thing for math majors. That math majors should have real analysis classes. They should also have algebraic structures classes. And I think they should have classes on topology and complex analysis as well. We're getting our topology right now. Topics in math is complex for those of you who are able to take that. Not all of you will be. We will, in that class, focus less on epsilons and deltas than this class, less on proofs. There will be some proofs. It won't be as heavy, though. We'll focus more on geometric interpretations using Mathematica. It'll be sort of halfway, and I think of it as halfway between multivariable calculus and real analysis. And I do think it is the most beautiful subject in math, even though I think chaos is beautiful too. I think complex analysis is the most beautiful subject, even though I didn't do my PhD in it either. It's just, it's beautiful because it's so geometric and so, there's so many unexpected things. Like, why would this ever be true? And it is. It's an amazing subject that way. And for student teachers who aren't going to be taking that class, I hope you watch the lectures anyway, because I'll probably give you your time. Just for fun, okay? Thanks for being in class. The course evaluations, again, are due by Sunday. I'm not sure if that means Sunday night or by Sunday right away, but probably Sunday night. Do them as soon as you can if you haven't done them yet, because it is technically required, not a credit. See you next Tuesday.